Thanks, Devavrat, for the introduction, and thank you to the organizers for the opportunity to speak here. So I'm going to speak about, three kinds of stochastic processes on networks. So today I'll talk about rumor spreading and first passage percolation. The second lecture will be on consensus and the voter model, and the last lecture will be on epidemics. Okay, so let me start first by describing two models. And let me also say, please feel free to interrupt if you have questions as we go along. So the first model we look at, we have the complete graph Kn. And on each of the edges of this graph, we put a weight We. And we are going to assume that these weights are IID exponential with parameter 1. And we are going to be interested in two quantities. So we pick two vertices I and j, and Wij is going to be the total weight of the shortest path between them. So it's the minimum over paths pi from I to j of the sum over edges in the path, We. I won't write down formally the definition of every term, but if anything's unclear, do stop me. And also, we'll be interested in Wi star, which is the maximum over j of these path lengths. So Wij is the shortest path from I to j, is the weight of the shortest path from I to j, and Wi star is the furthest, is the weight of the point which is furthest from I. Okay, so that's one model we are looking at, and another we are going to look at is rumor spreading. Okay, and here we start again with Kn as before, the complete graph on n nodes. And now, initially one of the nodes, node I, let's say, knows the rumor at time 0. And then the way the rumor propagates through the network is the following. So each node that knows the rumor propagates it at the increment times of a rate n Poisson process, okay, choosing who to propagate it, choosing the target uniformly at random. Yeah. Yeah, and these are independent of each other. Each node has its own rate n process.
And so that means that n is just simply the time scale.
Exactly. Yeah, so it might be more natural for you to want to think of a rate 1 Poisson process at each node, but there's a reason why I've chosen it to be rate n, and that's just a rescaling of time compared to a rate 1 Poisson process at each node. Okay, are these two models completely clear? Okay, so why have I chosen rate n? I want to convince you first off that these two models are exactly the same thing. Okay, and this is the rescaling I want for that to be true. Well, why are they exactly the same thing? So if you look at some vertex u, it learns the rumor at some time. It has a Poisson clock of rate n, and at every increment of this Poisson clock, it's going to pick who to talk to independently. So if you look at all the times at which u talks to v, they are obtained by splitting this rate n Poisson process here. So it's a Bernoulli splitting of this with probability 1 over n, it chooses v. So that gives you a Poisson process of rate 1 on every edge. That means the first time that u talks to v after it learns the rumor has an exponential 1 time. And so if we identify the weights of the edges with the times at which the rumor will propagate along the edge, they have exactly the same distribution and the same independence properties in the two models. And the memoryless property of the exponential plays a big role here. So the fact that at the time you heard the rumor, some time might have elapsed from the time it last talked to anybody is irrelevant. How long elapsed is irrelevant because the future time until it talks to somebody again is exponential, independent of that. Okay, so these two models are exactly the same. Okay, so maybe, yeah, let me introduce a bit more notation then. So let's define Tij to be the time for the rumor to reach j, starting from I, and Ti star to be the time for all nodes to learn the rumor. Then Tij has the same distribution as Wij, and Ti star has the same distribution as Wi star. Okay, so and this talk is going to be about what can we say about these distributions, and it's based on a paper of Svante Jansson, 99. I don't remember the full title, but it's 1, 2, and 3 times log n over n, something. Okay, I'll talk about the 1 and the 2, but not the 3 times. Okay, so let's start with a very simple calculation for the mean of these quantities, and then we'll look in a bit more detail about the distribution. Okay. So let's just calculate the mean of these quantities. It's maybe easier to think of rumor spreading, but you can think of whichever comes more easily to you. So let's define tau sub k to be the first time that k nodes know the rumor. So tau sub 1 is 0. At time 0, we start with node I knowing the rumor. And Ti star is the same as tau n, the time until all nodes know the rumor. Okay, so now let's look at the quantity tau k plus 1 minus tau k. So we have, at time tau k, k nodes know the rumor, and we want to know how long it is until one more node learns the rumor. Well, when k nodes know the rumor, there are n minus k that don't know the rumor, and there are k times n minus k edges between them. Each of them has an independent rate 1 Poisson clock. So the time until any one of these ticks is exponential with parameter k times n minus k. Yeah, because it's the superposition of this many rate 1 Poisson processes. Okay, and this very elementary observation is the basis for all our calculations. This is pretty much all you need for everything we are going to do. So if there are any questions, let me know. Okay, and also this is independent of the past. Okay, good. So the expectation of tau k plus 1 minus tau k is the mean of this exponential, and that's 1 over n times so that's the partial fraction expansion of 1 over k times n minus k. Okay, so now that gives us immediately the expectation of tau n, the time until all the nodes know the rumor, is just the, you can write tau n as this telescoping sum of tau k plus 1 minus tau k. And so this is the sum of the expectations. Okay, and that gives us that this is basically the sum of 1 over k between 1 and n is roughly log n, and this is the same sum in reverse order, so each of them gives a term of log n, and that gives us 2 log n over n. Okay, so this is the expectation of, so the expectation of Wi star, which is the same as this, is 2 log n over n. Okay, so this gives us Wi star. Now, what about Wij or Tij? So to calculate this, we want to look at how long the rumor started at I takes to reach vertex j. So here we are counting in order which vertices are reached, and for a specific vertex j, where in this sequence is it going to lie? It's going to have a random position in the sequence, and it's going to be uniformly distributed between 2 and n, right? So we are assuming you pick 2 vertices I and j and then realize the edge weights, which means that that particular vertex is uniformly likely to lie anywhere along the sequence. So this is just the same sum, k, okay, I'll take, so this is the sum, k equals 1 to, instead of taking the sum up to n minus 1, it's up to some random capital N minus 1 of the same quantity. Where n is uniform between 2 and little n. Yeah. So it's lying somewhere uniformly along the sequence. Okay, and then I have to take the expectation with respect to the randomness in N as well, in capital N as well. Okay. And if you do this calculation, you get that this is asymptotic to log N over N. No, this just comes from the fact that the order in which it's likely to be reached, all possible permutations are equally likely of who's who. Yeah. That's just the symmetry in the problem. Okay, so that's the mean of W. So the mean of Wi star is 2 log N over N, and the mean of Wij is log N over N, and those are the 1 and 2 in the title of Jonson's paper. And the 3 comes from if you pick 2 vertices, if you take the maximum over all vertex pairs Ij, how long does it take for the path between I and j? That's 3 log N over N, but I won't go into that. Okay, so we've calculated this mean. We could also calculate the variance. I won't go through the calculation, but if you do it, what you get is that the variance of tau n is approximately 1 over n squared, that's the scaling. Okay, times pi squared over 6. That's what you get. This comes from summing 1 over k squared, etc. Okay, there are 2 of them, pi squared over 3. Okay, and so this says that the mean of n times Wi star is asymptotic to 2 log n. The variance is bounded, and Wi star is bounded. So if you look at these, if you consider a sequence of graphs indexed by n, and you look at n times Wi star, these random variables, after suitable centering, they are tight. And so now we are trying to look at fluctuations of these random variables. And the fact that they are tight gives you hope that maybe they have a limit. Do the random variables? Okay, so this leads us to the following question. Does Wi star minus 2 log n, so do these sequences of random variables, do they converge in distribution to something? They don't have to, there might just be subsequential limits, but the fact that they are tight suggests that, well, it at least gives us hope that there might be a limit.
All of this at n-dot for occupied
No, but I'll say a little bit about that. Okay. And the time is there, good, thanks. Okay, I can go a bit further. Okay. So, so this is the question. So I'll now give you the answer, and then we'll spend the rest of the time proving that. So this is a theorem. Okay, so if you look at this sequence of random variables, then these converge in distribution. They do converge in distribution, and what they converge to is the sum of 2 independent Gumbel random variables. And if you look at, similarly, n times Wij minus that had mean log n. So if you center it at log n, it converges in distribution to the sum of 2 Gumbels minus a third Gumbel. So where lambda 1, lambda 2, lambda 3 are independent standard Gumbel. Random variables, and if you haven't come across this before, that means that the probability that lambda 1 less than or equal to x. So these have the CDF e to the minus x. Okay, and they are standard in extreme value theory. They come up a lot. Okay, we'll definitely have time to prove the first part of the theorem, and let's see about the second part.
Some of this 2 minus Gumbel, max over n minus 1 has to be the star.
Well, you kind of, the sum naturally splits into two parts. So we are going to start with a sum like this, split it from 1 to n over 2, n over 2 to n. Those both look symmetric. Each of them is going to give one of the Gumbels. The third, I don't have a very clear intuition for. I mean, you can show how it comes up, but okay. So I don't know how intuitive I can make it. But it comes from maxes of lots of exponentials, but we'll see how it comes up. There is dependence between, no, we are going to use the fact that we can express tau n as the sum of independent exponentials that look like this. That's going to be the, yeah, but you get two of them by splitting up this sum, okay? Okay, so let's start with this representation. So we have Wi star is distributed as the sum okay. So roughly, let's not worry about whether n is odd or even and so on. We can adjust the sum accordingly. So we have two sums. We are going to sum independent exponential random variables with parameter k and minus k. I don't want to introduce lots of extra notation for these random variables. So when I write this, I hope it's clear what I mean. And all these are going to be independent unless otherwise specified, plus the same sort of sum, n over 2 to n of the same thing. So these two things look the same. So let's call this first random variable x1 and the second random variable x2 and look at each of these. I want to simplify this sum by replacing the exponential k times n minus k with an exponential kn. So I want to split this into an exponential kn plus a little bit more. So let me state the following simple lemma about exponentials. So suppose lambda is smaller than mu, then you can write an x lambda random variable in distribution as the sum of an x mu plus a Bernoulli with parameter 1 minus lambda over mu times, okay, let me write tilde to say an independent copy of an exponential lambda. Okay, and the proof of this is easy. Yeah, everything's independent. All these three random variables coming here are independent. The proof is by picture. So let's put down a Poisson process of rate mu. Okay, so I have a rate mu Poisson process, and okay. So the increment times between these are exponential mu, independent of each other. I want an exponential lambda, so I want a Poisson process of rate lambda, so I just thin this by a parameter lambda over mu. So if I thin this, then I have to wait for some random number of increments of the original process, a geometric number of increments before I see an increment of my Poisson lambda process. So up to the first increment, I have an x mu here. And maybe I just have one and immediately I see it. The probability that doesn't happen is this bit. So that's the Bernoulli 1 minus mu that I have to wait a bit longer to see it. But how much longer do I have to wait? That's independent of the past. It's exponential lambda again. Okay, so I can use that to write x1 as the sum of exponential kn random variables plus an error term, which I'll call y1, where y1 is the sum of Bernoulli k over n times x k n minus k. Okay, and we can calculate the mean and variance of this y1 easily, and we can use that to show our second lemma, which is that y1 converges in probability to a constant, to log 2. Okay, and the proof is basically that the mean, the mean of n times y1 converges to this. All these random variables have to be scaled up by n to get what we want. Okay, so the mean of n times y1 is asymptotic to log 2. The variance tends to 0. And so Chebyshev's bound gives you this. Okay, so we've got rid of this nuisance term of, so we've got rid of this error term corresponding to these Bernoullis and exponentials. So essentially what we have got, okay, maybe we'll come back to this first sum. So now we are interested in the term sum k. The sum of the y1s is just a constant. So the sum of the x kn, we are going to multiply all our random variables by n. So let me take n times the sum. That gets rid of the n in the exponential. The exponential gets scaled up. It's a time scaling. So this becomes the sum of exponential k random variables. Okay. Now this we can express in terms of maxima of exponentials. So I'll state one more lemma to that effect. If you have the sum k equals 1 to n, let's say, of exponential k, this has the same distribution as the maximum k equals 1 to n of independent exponential ones. Okay. And again, why is this? This is straightforward. So we have these n independent exponential ones. Let's start from the right-hand side. Let's mark them, let's order them. So we have the smallest, the second smallest, the third smallest, etc., all the way to the nth. What's the distribution of the smallest of n independent exponential ones? This is exponential n. What's the increment from this one to the next, to the second smallest? Now there are n minus 1 left behind, and they are all independent by the memoryless property. The increment is exponential 1. So this is exponential n minus 1, and so on. Okay, so that yeah, it's well known, but I don't know who it's due to. It's very classical, so I don't know. Yeah, so this is kind of okay, folk theorem. I don't know. Yeah, they do. They do. I'll talk about that. Yeah. Only a little bit beyond, but they do. Okay, so I'm pretty much there. Okay, so yeah, so the maximum of, so the sum of these exponentials has the same distribution of them as the maximum of x1s. And the last piece I need to be able to prove my theorem is that if you look at the max of n independent exponential ones and subtract log n, this random variable converges in distribution to a Gumbel. And this proof is straightforward calculation. Okay, so let's ask, what's the probability that the max minus log n is smaller than x? Well, for that to happen, every one of them has to be smaller than log n plus x. So this is the product okay, so the probability of this event is 1 minus e to the minus that. So that gives you 1 minus 1 over n e to the minus x to the n, because there are n of them. And so this converges to e to the minus e to the minus x. Okay. Okay, so now this gives me all the bits and pieces I need. Okay, so that gives me the proof of the first claim of the theorem. Okay, so I wrote this Wi star as x1 plus an error term, I think, which I called y1, plus x2 plus y2. And what we have shown is that n over 2 times n times x1. We rescaled everything by n. N times x1 minus log n over 2, because it was the sum of n over 2 terms, converges in distribution to a Gumbel. And we showed that n times y1 converges in probability to log 2. Okay, so n times x1 plus y1 minus log n converges in distribution to a Gumbel. And the same for the other half of the sum. Okay, so that was the proof of the first half, the first claim in the theorem, that if you look at n wi star minus 2 log n, that converges to the sum of 2 Gumbels. The second part is a bit more involved. I won't go through the details, but in calculating the mean, we did something very easy. We just conditioned on the, we said it's the time at which j is uniformly likely to have any index of which vertex is reached. It doesn't seem that easy to use that to get this result. What you do instead is you want to start the rumor or the percolations from, so I start spreading the rumor, J starts spreading the rumor at the same time, and you look until the first time the two rumors meet. And roughly they'll meet after each of them has propagated it to square root n vertices. So, okay, so that's kind of the intuition. Instead, what you do is you start it at I, you propagate it till it reaches square root n vertices, look at how long that takes, then start the rumor at j, propagate it until it hits one of these vertices, see how long it takes, and there's a randomness in how long it takes, which gives you this minus gamma 3 term, and there's some inherent randomness in how long each of the rumor spreading processes themselves take, which give you the lambda 1 and lambda 2. Okay, it's a bit of a detailed calculation, but it's not hard, and it gives you this third term. The minus just comes from, okay, so it comes from the calculation. Yeah, but the number of samples, so let's say the first rumor has reached square root n vertices. So every time the second rumor is spreading, at each step it has a 1 over square root n chance of hitting one of those vertices. And the number of steps you need to take is therefore roughly geometric with parameter 1 over square root n. And if you look at the fluctuations of that geometric, that gives you the minus gamma 3 term. But yeah, but it's just a calculation. Okay, so so that was those were the main results I wanted to talk about, and one more which is not in Jonson's paper, which is about tail bounds. I'll mention something about tail bounds as well, which are not hard to calculate. Okay, I'm just going to talk about tail bounds for Wi star, the time to the time for the rumor to reach all nodes. So we had that the expectation of n times this was 2 log n. So let's fix some constant c smaller than 2. Then the bound we have, okay, I should look this up. So the probability that the rumor reaches everyone in much less time than you expect, this decays pretty fast. Okay. So you are looking at a fluctuation of size log n from the expected value, and the decay is doubly exponential in log n. So it inherits the double exponent. If you look at Gumbel random variables, their left tail is double exponentially decaying, and the right tail decays as a single exponential. And so you get exactly the same tail decay as for the Gumbel. The distributional convergence result doesn't imply it. It doesn't follow that the tail bounds are the same as the distributional bounds, but it's true for the left tail, and it's also true for the right tail. It turns out that that does pick up the right thing. So similarly, if C is bigger than 2, n times Wi star. So the right tail decays exponentially in log n. It's a single exponential decay. And it's what comes out again of the Gumbel. If you're familiar with the coupon collector problem, you'll know that this is also the kind of tail bounds on the coupon collector time. Okay. Okay, so those were the main results I wanted to discuss. There's one more thing, hop count. Yeah, this is also still the answer. Yeah, pretty much. Yeah, it's just using, okay, so he talks about this side, but not so much about this side in the paper, I think. But it's very straightforward from the same representations we had in terms of exponentials. He mainly focuses on the other two results, which are distributionally robust. And this I don't claim, I don't know, but I don't claim this is robust to the distribution. So we assume exponential edge weights. Most of the results go through. What matters is not, yeah, okay, I can just stop for the last 10 minutes. So what matters is not that the distribution is exponential. What matters is the density near 0. So the results are virtually the same if you have, let's say, a uniform distribution which has density 1 near 0. If you have any distribution which has strictly positive density at 0, then you just have to rescale time. You get exactly the same results. Sorry? That's right. Yeah. So, yeah. So, but we have the exponential has been used throughout the analysis. So we have to be careful. Yeah. Yeah. So we have to be a bit careful about when these results go through. So let me state a bit more precisely when that happens. So. Okay, so generalizations. So we assume that all the edge weights have RIID exponential 1. Okay, we don't need that. In fact, if the following is true, if the CDF of the distribution of the edge weights evaluated at x equals x plus little o of x. Then the expectation of wij and of wi star are the same. Okay, the results we stated for the expectations are the same. For the results for the fluctuations, we need a little bit more. So if we assume that the CDF is x, so the density is 1 at 0, plus something that decays a little bit faster, it's little o of x over log x, absolute value. Okay, then the fluctuations are Gumbel. So that result also holds. Now for the tail bounds, I don't know what assumptions you need, and it's not clear. Okay, you might need much stronger assumptions. And okay, again, intuitively, the idea is that at each step, what plays a role? So you have, at each vertex, you have n different edges going out of it, independent. And for short paths, most of these are not going to matter. You're looking at the minimum of these n things, or maybe at the log n smallest of these things. Nothing more than that is going to play any role. So all you're looking at is the log nth order statistic of these. And if they look just like those of the exponential, then you're done. And so it's only the density very close to 0 that plays a role. Okay, and then one can also look at the hop count. So you have your vertices I and j, and you're looking at the shortest path between them. And you can ask on that shortest path how many hops are there. Okay, so let's call Hij is the number of hops, so number of edges on shortest path from I to j. Well, let's look at, so we are starting the rumor from I. Okay, so first I contact some other vertex and informs it of the rumor. So you get, I directly inform some other vertex of the rumor. Now both of these are spreading the rumor. So the next vertex to be informed is equally likely to be informed by either one of them. Maybe it's informed by I again. And then the next one is equally likely to be informed by any one of these. Maybe it goes there again, then it learns from I, etc. Something like this happens. So what you have here is a tree that's growing randomly. And it's growing randomly according to the rule that the next vertex to be added is equally likely to be added to any previous vertex. And that's called a random recursive tree. Okay, so a tree growing like this is called a random recursive tree. And now the vertex j is, after you've grown this tree, it's uniformly likely to be any vertex. So what you're asking is, what's the depth of a uniformly chosen random vertex in this random recursive tree? And it's quite easy to write recursions for that. So let's define dk to be the depth of k. Okay, so depth of uniformly chosen vertex in random recursive tree with k vertices. So what does dk plus 1 look like in distribution? The k plus 1th vertex, okay, so you add one more vertex and then you uniformly pick a vertex. So the root has depth 0, then you grow from there, okay? And you're asking, okay, so the root cannot be chosen as your j, but let's ignore that for now. You're just uniformly picking a vertex. So when you've added the k plus 1th vertex, and then you're randomly picking a vertex, with probability k over k plus 1, okay, so with probability k over k plus 1, it's a pre-existing vertex, which has the depth dk. And with the residual probability, it's the new vertex which was added uniformly at random everywhere. So it has depth dk plus 1. Okay, so this is equal in distribution to dk plus Bernoulli 1 over k plus 1. So there's a very simple expression for the depth of a randomly chosen vertex in this tree. You can calculate its moment generating function, etc. And if you do that, you can show that this depth, and hence also the hop count, satisfies the following property. So the hop count hij minus log n over square root log n converges in distribution to a standard normal. Okay. So the hop count is log n plus a Gaussian fluctuation. Good, I'm on time. So yeah, that's all I wanted to say for today.
Yes.
Have you done calculations on other kinds of graphs like
No, so there's been a lot of work on percolation on lattices, obviously, but this is the other class of interesting models. So yeah, the abstract promised a bit more, which I didn't mention, but since you asked the question, this model and the other model, so this is called the stochastic mean field model of distance. And there's been work by Mezard and Parisi in the mid-80s who looked at a number of combinatorial optimization problems on this model. So for instance, the minimum spanning tree and the traveling salesman and so on. And they gave, well, some arguments for the limiting values of the weights of these random objects. And since then, people have more rigorously proved some of these results. For instance, if you look at the minimum spanning tree on this edge-weighted model, that has a limiting weight of zeta of 3. Zeta is the Riemann zeta function. If you look at this shortest path tree that we grew here, the total weight of this, the limiting weight of that is zeta of 2, which is pi squared over 6. There are limits for the traveling salesman problem, etc. So this is considered an interesting model for various combinatorial optimization problems as well.
Yeah.
Can you quickly tell us the relation between Hij and dk again?
It's exactly, so yeah, sorry, Hij is the same as dn. You add all n vertices, and then the jth vertex J is uniformly likely to be anywhere here. Yeah.
You mentioned earlier that you talk about generalization to
Sorry, yes. Yeah. You asked this question early on. Yes, sorry, I forgot about this. Well brought up. Okay, so these results, so this we did for the complete graph. If you look at dense enough heterogeneous random graphs, so well above the connectivity threshold, then essentially these results carry through with a suitable rescaling. Because of what I mentioned, that you never look at any edge which is not the 2 log nth or the 10 log nth shortest edges at a vertex. And if you restrict yourself to those edges, what you get from the complete graph is an heterogeneous random graph. So those carry through. But for other graphs, this doesn't carry through. For things which are far from exponential, this doesn't carry through. But Remco, who's going to speak here next week, possibly on quite different topics, he has a whole series of papers with a number of different authors. Shankar Bhamidi is on several of them. And they have looked at this on other graphs where different things happen and there are different universality classes. And they have maybe not complete, but a very broad picture of what happens in different settings. And there you have to, it was possible to do all this using extremely elementary techniques. What's needed there is mostly you are looking at branching processes. You have to look at branching processes in a fair bit of detail, and yeah. Yeah, Manjunath. This one? No, it's a calculation. So, okay, so I gave you this representation of dn in terms of the sum of Bernoullis, independent Bernoullis. dn is the sum of Bernoulli 1 over k plus 1. So you do moment generating function calculations, and yeah, it's just a calculation that it's that.
Okay, if no more question, then let's thank Ganesh again.